We now move on to section 6.10. We're going to talk about a new kind of function called a hyperbolic function. Typically in math, when we define new functions, it's because they're useful to us. That's why the natural log and exponential functions not only were discovered, but why we gave them names and kept them around. They turned out, as we saw in the last section, to have a lot of uses. Certain combinations of natural exponential functions also occur very frequently in applications. And when something happens a lot, it's nice to give it a name so that we can refer to it easily without writing out a complicated formula. The specific ones we're talking about right now are what are called the hyperbolic functions. And you'll notice that the naming convention is very similar to the naming convention for the trig functions. That might seem odd, and we'll talk about that a little bit later on, but we're going to find out that there are a lot of similarities between the way these functions behave and the way the trig functions behave. So the naming convention was natural for that reason. All right, first of all, the two basic definitions. We define the hyperbolic sign, abbreviated sin h of x, as e to the x subtract e to the minus x over 2, and the hyperbolic cosine of x, e to the x plus e to the minus x over 2. Just for speed, because hyperbolic sine and hyperbolic cosine are kind of a mouthful, you will typically hear people refer to these as sinh and cosh. And I probably will too, so I don't get tongue-tied. All right, after that, the rest of these definitions, again, follow the same convention that trig functions do, right? Hyperbolic tangent, sinh over cosh. Hyperbolic cosecant is the reciprocal of hyperbolic sine. Hyperbolic secant, reciprocal of cosh. And hyperbolic cotangent, the reciprocal of hyperbolic tangent. So the same kinds of relationships as we see for trig functions. We're going to go ahead and find some of the other similarities here in the next few problems, starting with, let's just evaluate by hand, sinh of 0 and cosh of 0. Hyperbolic sine of 0, if I just plug 0 into my function, would look like that. And of course that's 1 minus 1, or 0 on the top, giving me a value of 0 for the hyperbolic sine of 0. How about the hyperbolic cosine of 0? Well, again, just plug 0 in. That'd be 1 plus 1, or 2 over 2, and that's 1. The parallels with trig functions continue, right? We also know the sine of 0 is 0, and the cosine of 0 is 1. So this also seems to hold true for the hyperbolics. All right, just like we have trig identities, we also have hyperbolic identities. Be a little bit careful with these. These are similar but not identical to the trig identities. For example, look at this very first one, right? For the trig functions, it's cosine squared plus sine squared, that's 1. For the hyperbolics, it's cosh squared minus sinh squared, that's 1. So a lot of these are very, very similar, but one sign is different. One SIG, positive or negative sign, will be different. Here's a list of hyperbolic identities. There are more, but these are probably the ones that we would be most likely to come across or use. So I've put them in here. And just like trig identities, you can actually prove hyperbolic identities as well. So let's do one for starters. I'd like to verify the hyperbolic identity cosh squared t minus sinh squared t equals 1. I'm going to start by saying, well, really right now all I know is the definitions. So I'm going to go back to these, and I'm just going to put in cosh of t and square it minus sinh of t and square that. So that would be e to the t plus e to the minus t over 2 squared for cosh squared t. And then for sinh squared t, I'll have e to the t subtract e to the minus t over 2 squared. And I want to prove that that equals 1. Let's square this out. We'd have e to the t times e to the t would be e to the 2t. Plus, when you multiply the inners and the outers, you're going to get e to the 0, and you'll get that twice, once for the inners and once for the outers. Plus e to the negative t times e to the negative t would be e to the minus 2t over 2 squared is 4. And the same analysis over here. E to the 2t, subtract this time 2e to the 0, plus e to the negative 2t, also over 4. Since we are subtracting, notice here with the common denominator, e to the 2t subtract e to the 2t is 0, and also e to the negative 2t subtract e to the negative 2t is 0. So I end up with a positive, that's e to the 0 is 1, so I end up with a positive 2/4, subtract a negative 2/4, and of course that's 1/2 plus 1/2, or 1, which is exactly what I was supposed to get. Any trig identities can be proven in this way, just by substituting what the functions are actually equal to, or by using other accepted trig identities to inform our proofs. All right, we'll come back to that actually, I believe, in just a little bit. In part B, we know our trig functions are sometimes called circular functions. And the reason for that, of course, has everything to do with the unit circle. I just want to kind of remind you where that name came from. Remember that when we say sine squared theta plus cos squared theta equals 1, we usually think of sine theta as the y value on the graph and cos theta as the x value on the graph. So we're really just saying y squared plus x squared equals 1, which is the equation of the circle of radius 1, or the infamous unit circle. When we locate a point on our unit circle, if we have this angle theta with the positive x-axis, then the point on the circle has coordinates x, which is cos theta, comma y, which is sine theta. So, what I'd like to do now is use a similar analogous substitution for the hyperbolic identity that we've just verified. What graph would we be able to draw and label based on that identity? Well, remember the identity back from part A was cos squared t minus sinh squared t equals 1. If I, kind of like I did here, where x was cosine theta and y was sine theta, if I let x be cos t and y be sinh t, then this would just say x squared minus y squared equals 1. That's not the graph of a circle. What's that the graph of? Let's take a quick peek at Desmos and find out. If I graph x squared minus y squared equals 1, notice what I get here is a hyperbola, not a circle, right? So, does it now start to make sense why we call these the hyperbolic functions? The associated graph's not a unit circle. Instead, it's a hyperbola. And notice that the x-intercepts of this hyperbola are 1 and negative 1. I'm going to sketch that. And in fact, on this graph, at any particular point, what we have is for the x, that was what we defined as the hyperbolic cosine, right? X was hyperbolic cosine, so the x value is the hyperbolic cosine. Y was the hyperbolic sine. It's hiding here behind my graph, but y is hyperbolic sine. So for this point right here, which is like an angle of 0, hyperbolic cosine is 1, hyperbolic sine is 0. Not unexpected, right? It's what we saw in the first example that we did today, but also mimics that whole idea of the trig functions. If you come around 180 degrees over here, or pi, it must be that the hyperbolic cosine of pi is -1, and the hyperbolic sine of pi must be 0. All right, there is a big difference between the hyperbolic functions, though, based on this graph, and the circular functions. For a circular function, I think I can go back here now. For a circular function, once our theta goes all the way around to 2 pi, the values on the unit circle just start repeating themselves. And that's what causes the function to be periodic. Right? Will hyperbolic functions be periodic? In fact, they actually will not. What happens with a hyperbolic function is that if we continue to get larger and larger t values, we're going to continue to go out further and further along a branch of the parabola. So these are periodic because as theta increases, we go back around our unit circle. And the x and y values, or in other words, the cosine and sine values, repeat. That's what causes the periodic nature of the trig functions. This is not going to happen with hyperbolic functions. As the t values increase, we'll simply go out further along the hyperbola. These don't repeat. So that's one big difference between the trig functions, the circular functions, and these hyperbolic functions. Trig functions are periodic, hyperbolic functions are not. In fact, here are some graphs of some of these hyperbolic functions. I would not expect you to remember these or memorize them or anything, but your calculator can generate them if you need them. But right here, we've got the hyperbolic sine. Notice that as x gets bigger, we keep on going out and up. As x gets smaller, out and down. That would be the graph of the hyperbolic sine function. Hyperbolic cosine is over here. Hyperbolics for tangents, cosecants, secants, and cotangents are all there. I put them there simply for informational purposes. Again, if we ever actually need them, we'll have to generate them with a calculator. They're not graphs that most people have memorized or anything like that. All right, let's go back to this idea of verifying identities. In example 2, we would like to verify some hyperbolic identities. And this time, instead of necessarily going all the way back to the beginning, we're going to go ahead and we're going to make use of some of the identities that were listed for us. So I'm going to take these identities as givens now, and based on these, we're going to try and verify those. So, first of all, In this first identity, I have the hyperbolic cosine of 2x. Probably a good idea just to go ahead and substitute that for it right there. Oh, wait a minute. Then I'm already there. Maybe I did want us to go back to the beginning. I'm sorry. I did want us to go back to the beginning. Otherwise, I think we are too quick here. Let's go ahead and do that. Hyperbolic cosine of 2x. Right? Well, let's see. That would just mean plugging in 2x instead of x in my definition of hyperbolic cosine. So I'd have e to the 2x plus e to the negative 2x over 2. And I want to show that that is equal to hyperbolic sine of x squared plus hyperbolic cosine of x squared. This is pretty much in simplified form already, so I'm just going to leave it like this. Let's work at the right-hand side. First fraction would be e to the 2x minus 2e to the 0. And then negative times negative would be plus e to the negative 2x over 4. Plus the second one, e to the 2x plus 2e to the 0 plus e to the negative 2x over 4. And let's see, what do we get this time? The negative 2e to the 0 and the positive 2e to the 0 are being added, so that's just 0. And I would have 2e to the 2x plus 2e to the negative 2x over the common denominator of 4. And of course I could factor out the 2 and divide it with the 4 in the denominator, so basically I'm dividing by 2 over 2, and that's going to give me exactly what I wanted. Those are equal, and we're good to go. All right, let's try one more. This is actually this identity right here, but we're going to try and prove it now. And I'm just going to use a spare sheet of paper here since I kind of ran out of space. All right, hyperbolic cotangent of x squared minus hyperbolic cosecant of x squared needs to be equal to 1. This time, I think I might actually be able to get away without having to go all the way back to the E definitions. This time I think I can use some things I already know to help. So let's see here. I'm going to start by saying the hyperbolic cotangent would be cosh over sinh. Again, notice the similarities to regular trig functions. Cosine over sine is cotangent. Cosh over sinh is hyperbolic cotangent. Minus hyperbolic cosecant would be 1 over hyperbolic sine of x. Square that. And I'd like to show that this is equal to 1. All right, I'd have cosh squared x minus 1 squared is still 1. And I'm going to put that all over the common denominator of sinh squared x. All right, at this stage, I'm going to do just a little bit of using an identity that we already proved, right? We already proved that one. And I'm going to say, if I swapped the places of the 1 and the hyperbolic sine, what would happen? We know cosh squared x minus sinh squared x equals 1. So actually I could even do it this way. Cosh squared x then would be 1 plus sinh squared x. And I can plug that in right there. I then have this minus 1 over the denominator sinh squared x. And of course, 1 minus 1 is 0. And then sinh squared x divided by sinh squared x would give me the 1 that I'm looking for. Right? So when you prove identities, notice that the technique's very similar to what we were doing for trig back in calc or pre-calc actually. You always want to work with the two sides separately. Oftentimes one side's already simple enough and you don't do anything with it. You work everything on the other side. We did the same thing over here. We kept the one side the way it was, did everything on the other side. And ultimately your goal is to get the two sides to match in the end. So that's verifying identities. Didn't think that was going to come back to haunt you, did you? All right. Let's talk about calculus for these hyperbolic functions. Again, unsurprisingly, the derivatives and integrals are going to be very similar to the derivatives and the integrals for regular trig functions, but the signs, S-I-G-N-S, are going to be slightly different. We're going to go ahead and we're going to do one of these kind of out by hand, and then the rest of them we'll just kind of accept. I'll tell you what they are. So let's figure out from the basic definition what the derivative of hyperbolic sine x would be. I'm suspicious that it'll be something like hyperbolic cosine, since that's the derivative of sine, right? It's cosine. But let's see. If I take the derivative, and I'm just going to put in the definition of the hyperbolic sine here, the 2 in the denominator is just a constant, so I can just think of that as a multiplier of 1/2. And then the derivative of e to the x is e to the x minus the derivative of e to the minus x, which is itself, and then times a -1 for the chain rule. And that's going to give me e to the x minus a negative is plus e to the minus x over 2. And that is indeed just the definition of the hyperbolic cosine of x. So the derivative of sinh x is cos x. Right? You could go through and do that same type of analysis for any of these, and I won't take the time to do all of them out on the video. You can play with them or look in your book if you'd like. But I'm just going to tell you that it goes the other way as well. The derivative of cos x turns out to just be sinh x. Notice that's slightly different from the trig version, right? For trig, the derivative of cosine is negative sine, but for the hyperbolics, the derivative of cos x is sinh x. Derivative of the hyperbolic tangent is hyperbolic secant squared x. Again, very similar to the trig version. And the derivative of cotangent, hyperbolic cotangent rather, is negative hyperbolic cosecant squared x. Those two look almost identical to their trig versions. Derivative of secant hx turns out to be negative hyperbolic secant x, hyperbolic tangent x. Again, similar to the trig version other than the negative sign. And then finally for the hyperbolic cosecant, we end up getting negative hyperbolic cosecant x, hyperbolic cotangent x. So other than being a little careful with your positives and negatives, which are slightly different, the hyperbolic derivatives are very similar to the trig derivatives. All right, let's actually find a few derivatives that involve hyperbolic functions. I want to start with the derivative of hyperbolic sine of x squared minus 3. According to the little table that we just filled out over here, derivative of hyperbolic sine is hyperbolic cosine. And then, of course, you'd have your chain rule, so we'd end up multiplying by 2x. And just like with trig functions, we prefer to have the multipliers in front of the hyperbolic. So I want to write that as 2x cos x squared minus 3. right, in B, we have x cubed times natural log of cosh x. This is going to be a product rule. So I'm going to set this up with the f is x cubed, and the g is natural log of cosh x. F prime would be 3x squared. And g prime, the derivative of the natural log is 1 over the argument, cosh x, times for the chain rule, derivative of cosh x is sinh x. So I actually have sinh over cosh. That would be the hyperbolic tangent of x. All right. Little f prime, remember it's going to be fg prime plus gf prime. So I'd have x cubed times the hyperbolic tangent of x plus gf prime, 3x squared times that natural log. All right, one more derivative to practice here. The function is the hyperbolic sine squared of 3x. And just a reminder, it's probably best to think of that as the hyperbolic sine of 3x all squared. Makes it easier to see the chain rule when you think of it that way. So for my derivative, I'm going to start with the power rule. 2 times the hyperbolic sine of 3x to the first power. And then my chain rule, the derivative of hyperbolic sine 3x is hyperbolic cosine 3x. And then one more chain rule, the derivative of 3x is 3. So I end up getting 6 sinh 3x cosh 3x. All right, so there's some derivatives with our hyperbolics. And right here we're going to do an application of the derivative, another one that you maybe haven't seen since Calc 1, but good time to review it. I'd like to find the relative extrema, that is the max-mins, for the function x cosh x minus 1, subtract sinh x minus 1. Okay. This is where we use that first derivative test. We start by locating our critical points, where f prime is 0. So let's go ahead and do our f prime. Looks like I will have a little product rule right here. I'd have to have f is x and g is cosh x minus 1. Oops, sorry, you can't see that. Pull that down. So f prime would just be 1. And, oh my goodness, I left off the h. It's not cosine, it's hyperbolic cosine. G prime then would be hyperbolic sine x minus 1. There is a chain rule here, but the derivative of the inner function is just 1, so I won't bother writing times 1. And so, my f prime, fg prime, x, hyperbolic sine, x minus 1, plus gf prime, hyperbolic cosine, x minus 1, and that's my product rule right there. All right, the derivative of the second term, minus, and that'll become hyperbolic cosine, x minus 1. Again, the chain rule would just be a times 1, so I won't write it. And that has to equal 0 if this is really going to be a critical point. This was very helpful, the fact that the hyperbolic cosines add up to 0, so those are gone. And so I just end up with x sinh x minus 1 equals 0. So either x equals 0 or the hyperbolic sine of x minus 1 equals 0. You may remember we saw before that the hyperbolic sine of 0 is 0 was one of the very first problems we did. So this is going to be true if x minus 1 is 0, or in other words, if x is 1. All right, let's test this. We want to know if these are maximums, minimums, or neither one. My critical values are 0 and 1. And I'm testing f prime. We have not put our hyperbolics into the calculator yet. I should probably show you where that is. Let's go ahead and put f prime in. So our y equals, and we're going to put in the f prime, which is x times the hyperbolic sine of x minus 1. To get the hyperbolic sine, what I usually do is just use the catalog. Catalog is above the 0 key, so second catalog. And you can scroll all the way down to the s's to find hyperbolic sine, but it's actually much easier to do if you just find the key with the s above it. It's actually the ln key. See the little s above it? Just hit that, and it'll automatically take you down to the s's, and then you don't have to scroll so much. There it is, hyperbolic sine of x minus 1. There's a lot of things in the calculator that I don't use that often, and if I don't know where else it is, I can always find it in the catalog that way. All right, so there's our derivative function. It's in here now. I'm going to go to my table. And let's see here. I need to pick a test value over here, like maybe -1. And that is positive. Let's try something between 0 and 1, like a half. That has a negative value for the derivative. And then something over here, like maybe 2. And I guess the light's over here, but you can see that when I plugged in 2, the derivative was positive. So my conclusions would be that I have a maximum at x equals 0, and then I have a minimum at x equals 1. You could go back and plug into the original function to get the y values, but I'm just going to leave this one like this. All right, let's finish this discussion of the hyperbolic functions by talking about an application. I want to talk about the catenary curve. The catenary curve, and this is just culled from Wikipedia. I know it's not always the most accurate, but I think this information is pretty good. In physics or geometry, a catenary is the curve that an idealized hanging chain or cable assumes under its own weight when supported only at its ends. So if you could imagine like picking up a rope or a cable or something like that and putting one end in each hand, the curve between your hands would be a catenary curve. The curve has sort of a wide U-like shape. It's superficially similar to a parabola in its appearance, although mathematically it's actually quite different. This same shape appears in the design of a lot of arches and is a cross-section of what's called a catenoid, the shape that's assumed by a soap film, bounded by two parallel circular rings. Mathematically, the catenary curve is actually the graph of the hyperbolic cosine function. And that's what I really want you to take away from this. These two things. A catenary is a curve that a hanging chain or cable assumes when supported only at the ends. And mathematically, its graph is a hyperbolic cosine. So, here's an example. Suppose we've got this power cable here. It's suspended between two towers, so you can consider those the ends. And that forms this catenary curve in here. The equation for this particular catenary is 12 plus 10 cosh x over 10. If we're told that the distance between the two towers is 20 feet, my goal is to find the slope of that catenary curve at the point where the cable meets the right-hand tower. So I'm going to put in a couple of things to help us out here. First of all, I need a coordinate system. One is actually suggested for us in this picture. I'm just going to highlight it a little bit. Notice they kind of gave us a y-axis here and an x-axis here at ground level. And since the towers were 20 feet apart, they've put one of the towers at -10, and they put the other tower at +10. So a total distance of 20 feet in between them. Then this curve, from the top of one tower to the top of the other, is our catenary curve. Ultimately, my goal is to figure out the slope of the tangent line to that catenary, right here where it meets this tower. So I could sort of sketch in the tangent line, and I want the slope of that tangent line. It's what we sometimes call the slope of the curve, but it's really the slope of the tangent. Right? Well, we know the slope of the tangent is simply the derivative. So dy dx. And in this case, the derivative would be 0 plus 10 times the derivative of cosh x over 10 is sinh x over 10 times my chain rule would be 1/10. My 10s can divide out here, so I just get hyperbolic sine of x over 10. Since I specifically want to know what that slope is at this point, at this particular point, the x value is 10. So I'm going to get the hyperbolic sine of 10 over 10, or sinh 1. And again, you can just plug it in your calculator. Plugging these in is a little bit of a pain because you have to go to that catalog to get that hyperbolic sine, so I'm going to tell you that I did. And I got about 1.175 for my slope. One of the reasons that things like this are so important is because we know we usually don't want a cable to have too sharp an angle. That tends to lead to things like the breaking or cracking. And so knowing things like that slope is helpful when you're imagining a construction like this. All right, we're ready to leave derivatives and talk about integrals of our hyperbolic functions. All of these are simply going to be the reverse of the derivative rules. So sinh and cosh are each other's derivatives. They are also one another's integrals. Integral of sinh x would be cosh x plus c. Integral of cosh x would be sinh x plus c. Oops, I said an h there. Integral of the hyperbolic secant squared of x is tangent hyperbolic of x plus c. Boy, I'm missing my h's. Integral of hyperbolic cosecant of x squared dx is actually negative hyperbolic cotangent of x. This guy would be negative hyperbolic secant of x. and that one is negative hyperbolic cosecant of x. And again, these are just literally the reverse of the derivative rules. So these are the only ones we can do. We have to match one of those exactly in order to actually find an antiderivative. Let's try a problem or two like that. My first one, I'd like the x times the hyperbolic cosine of x squared dx. Our usual type of u substitution is going to work just fine here. If u is x squared, then du would be 2x dx. And 1/2 du equals x dx. I have the x dx right there. So I can rewrite this as cosh u. And then I replace the x dx with a 1/2 du. Integral of cosh u is sinh u. And I'm going to put the u back in, that's x squared. So all of our usual rules for integrals, u substitutions, all that kind of stuff still applies. Let's do one more. And then we'll finish with a last application. All right. We have the integral of cosh 2x, sinh squared 2x dx. I'm going to start by rewriting this as cosh 2x times sinh 2x squared, because it emphasizes that this sinh 2x is inside the squaring function, making this a good candidate for my u. So du would be cosh 2x and times 2 for the chain rule dx. And I have 1/2 du equals cosh 2x dx. I've got that cosh 2x dx right there. So I can rewrite my integral as u squared. And the cosh 2x dx I'm replacing with the 1/2 du. Integral of u squared would be 1/3 u cubed. And so I actually end up with 1/6, and then the cube of the hyperbolic sine function, plus c. Hopefully these integrals and derivatives are looking pretty familiar to you, not because you've known something about the hyperbolics before this, but simply because they're so similar to the same techniques that we used when we were integrating trig functions. All right. To wind this section up, we're going to talk about another application. Again, I've got my power cables suspended between my two towers 20 feet apart, and there's that catenary equation that describes that curve. I'd like to now find the length of the cable between the two towers. So this time, I actually want to know, what is that length? Remember that we usually call the length of a curve or an arc S. So I'm just going to label that S. And I'll remind you, because we haven't talked about it for a little while, we had the arc length formula, which is the integral from a to b times the square root of 1 plus the derivative dy dx, or f prime of x squared dx. Right? It's on your list of formulas. It's one that we've studied back in, I think it might have been 6.6 or 6.5, something like that. So in this particular case, this curve is going between negative 10 and 10. And we'd have the square root of 1 plus the derivative, at 0, that would be 10 hyperbolic sine x over 10 times 1/10 for the chain rule. And that derivative gets squared. And I'd have the dx. I'll squeeze that in down there. So under my radical, I've actually got 1 plus sinh squared of x over 10. Now, I think we can actually go a bit further with this, because that's just like one of our identities, isn't it? 1 plus sinh squared. If I move the sinh squared to the other side, that would just be cosh squared. So I can rewrite this as the square root of cosh squared x over 10. Which is really nice, of course, because now I can just take that square root and I just have the integral of cosh x over 10. We can do just a little u substitution here. If u is x over 10, then du would be 1/10 dx, and 10 du is equal to that dx. So the integral of cosh u, and I'll replace the dx with 10 du. Extra space here. And let's see, the integral there would be 10 times the hyperbolic sine of the u, which is x over 10. And this was supposed to go from negative 10 to 10. So I'd have 10 times the hyperbolic sine of 10 over 10, which is 1. Subtract 10 times the hyperbolic sine of negative 10 over 10, which is negative 1. And I just plugged all of that in my calculator, and I ended up getting 23.5. And I guess these distances were in feet. So the towers themselves were 20 feet apart, but of course, due to the sag of the cable itself is going to be a little bit longer than that. Turns out, in this case, to be 23.5. All right, that brings us to the end of our discussion of the hyperbolic functions. We're going to talk about the inverse hyperbolic functions in the next video.